Hello everybody, and we're back for a final installment of Callum's video lectures for March 19th. So, we're going to get around to finally learning about an apportionment method. This one's called Hamilton's method. It's also known by many other names, but this is section 4.2 on Hamilton's method. Put up some of those other names here because we'll see them sometimes, aka Vinton's method, because it was actually proposed, it was actually put into effect in 1850 when a guy named Vinton proposed, really pushed it as saying these previous methods we've been using have not been working. Hamilton's method is the first pretty good apportionment method that we started using in the United States. Once we had fixed the number of representatives in our house, that's one thing. At first, the number of representatives in our house wasn't fixed, so you couldn't exactly call it apportionment when there isn't a fixed number of seats that you're apportioning. But in 1850, we started using Hamilton's method. I'll go back to that little thing. So here, our first method, the rejected fractions method, was much like Hamilton's method without the third step, which we'll talk about soon. But that wasn't working out very well. So then they started using this major fractions method, which we also won't talk about because it's a bad one. Hamilton's method is this one, this greatest fractions method here, and it was used in our country for 61 years there, and until we noticed some funny things were happening. But so it's also known as Vinton's method. It's also known as the method of greatest fractions. Or largest remainders. What a lot of pseudonyms. Remainders. Okay. So I will start out by just kind of explaining what this method is, how to use it, why it's better than just trying to round to the nearest integer like we tried in the last video lecture, and well, we'll use it on that example and see how it works. So it's quite a simple process, really. There are 3 steps. The idea. So there are 3 steps. One, we're going to just calculate everybody's standard quotas, just like we were doing for our fictional example. So 1, calculate standard quotas, and we'll recall what those are in just a little bit. The second thing we're going to do is give every state at least 1 seat, and give those with standard quota larger than 1, their lower quota. So I don't want that to confuse you. Basically, all I'm saying is give every state their lower quota, but if giving a state its lower quota leaves them with no representatives, for instance, what would happen to Vermont because our population is too small, Vermont gets a representative. Just from this, every state gets at least 1 seat. Yes, we have 1 seat in our House of Representatives, not because our population is big enough. We have 1 seat just because we are a state that deserves to have a seat, even if our population is quite small. Okay, but once we've done that, this is essentially like rounding everybody down in our previous example. So this will give us a smaller number than the total number of seats available. So we'll have a surplus. So we're going to divvy up those surplus seats. Divvy up. Or why don't I say assign the surplus seats. One at a time. To the states. To the states with largest fractional part or residue or remainder. With largest remainder. So remember the remainder to the states with largest remainder on their standard quota. Their standard quota. Good. So this is the process. We're going to calculate standard quotas. That is, calculate how many seats every state should get if we were allowed to give away fractions of a seat. We're not allowed to give away fractions of the seat. So what we're going to do is we're going to make sure every state gets at least one seat, and then we're going to give all of the other states their standard quota rounded down. Okay? So now that we've rounded all of the standard quotas down, except for a few of them, the very small ones, now that we've rounded almost all of the standard quotas down, we will have surplus seats to give away. We might give away exactly the right number of seats like this if everything divides up evenly. But in most cases, we will be giving away fewer seats than the total number of seats that we have. And so with those surplus ones, what we're going to do is we'll look at the fractional parts. We'll look at the remainders when we calculated those standard quotas. So then we'll look at the fractional parts, and the biggest fraction, the states with the biggest fractional parts will get the surplus seats first, and we'll go down that list one by one. Why don't we go back to our example? Good. So back to Parador. Ooh. So I assume that you were watching the last video before this. Why don't I go down to our example here, and I can just copy and paste our little table here. Let me just do that. Okay. Whoa. Let's make that smaller. Maybe I should have... Here. Why don't I put it down here? Okay. Good. So remember that our standard divisor, SD, is 50,000 here. And we had our standard quotas for each state according to the table that we had it. And our first attempt was just to do some basic rounding and see what happened. Well, it didn't work. If we rounded everybody to the nearest whole number, we ended up trying to give away more seats than we had to give away. So basic rounding we decided was not an apportionment method. But let's go back and let's try this with the Hamilton method, or the method of greatest fractions. Okay, so the Hamilton method. Let's see. Let's go back to our steps. Well, step 1 was to calculate the standard quotas. We've already done this. Good. Now, step 2 will be, let me continue our table. Just like this. Now, the step 2 was to give every state their lower quota if they get one seat. So, because every state has a population, has a standard quota above 1, we don't have to worry about every state getting at least one seat. So we can just give everyone their lower quotas, right? Lower quota. And remember that the lower quota was just the standard quota rounded down. So now, instead of 33, like normal rounding would give us, state A will get a lower quota of 32. State B will get a lower quota of 138. State C will get a lower quota of 3, which does match what it should have been rounded to. State D will get a lower quota of 41. E gets 13. And F gets 19. Okay. Well, let's see what happens when we add all of these things up. What do we get? We'll get 2 and 130 at 140. That gets 170. 170 plus 60 gives us 230. 230, 243, 246. Okay, so this gives us 246 in total. So what does that mean? It means we have 4 surplus seats to give away. Let's stop worrying about the standard divisor for now. So how are we going to give away our surplus seats? Well, Hamilton. Apportionment. Well, let's look. So if we have 4 surplus seats, we want to find the 4 states with the largest fractional parts. Another word for fractional part or remainder is residue. You might see the book use the word residue, but that doesn't mean anything different than these. Okay, so what are those? In order, the first highest fractional part seems to be state A with 0.92 as a fractional part. Second highest, if I'm looking just at the decimals now, right? I'm just looking at the decimal points because we've already given everyone their lower quota. So state D, next highest is 0.82. It's just lower than 0.92, but the next highest here is 0.76. And finally, the fourth highest is 0.72. So that means that each of these 4 highlighted states, A, B, D, and F, are going to get one of the surplus seats. So, in the end, our Hamilton apportionment will be 33, 139, 3, 42, 13, and 20. And sure enough, we had 246. We gave 4 more seats away, and this should give us 250. Good, exactly what we wanted. So that's how the method works. At first glance, I think it seems quite intuitive, and I hope it seems quite intuitive to you as well. If we can't be sure that just normal rounding will always give us the right number of seats, well, we can be sure that if we round everybody down, that we'll have enough seats, at least, right? Maybe too many. But then if we have a method for giving away those extra seats, and a method that does that in a seemingly fair way by taking the largest fractional parts of each of each of the states, well, it just seems like a logical explanation to me, and it seemed like a logical explanation to most of America until about 1911, when somebody noticed something called the Alabama paradox. So, is this a good method? At first glance, it may seem so. However, now I want you to consider this example. So this is a fictional example again, but it is based on a very real example. A real example, which is the reason that we no longer use Hamilton's method in our House of Representatives. So, even though some of the numbers have been fudged to make things more manageable for us as we ease into calculating apportionment. Sorry, kind of lost my. Yes, so it's just a simplified version of what happened in Alabama. So this is a simplified version of the Alabama paradox. Okay. So we have a country. And that country has 3 states, say. A country has 3 states. And we will call those states Bama, hint, hint, Alabama. I don't know what the other names they gave them were kind of random. I think they said Tecos. And what is this? Illinois. They used weird names. It doesn't really matter. We might as well call them A, B, and C, but for now we'll call them Bama, Tecos, and Illinois. Okay, and I guess for like Texas and Illinois, Alabama, Texas, and Illinois, I guess is where they're taking those from. Anyway, let's make our little chart kind of similar to how we were doing it before. So let's write down their populations here. So we have population and here we'll have a total column. Okay. So population of Bama we're going to say is 9,400. We'll say that the top population of Tecos is 90,300, so a good bit bigger. And of Illinois, we'll say it's 100,300. And so in total, this country has 200,000 people. Okay? So we have a country with population. Why don't I move this down a little bit and I can write... oops, that's not going to work. Move this down. So why don't I say it has population so a country of 200,000 people. A country of 200,000 people has 3 states. Their populations are divided up respectively like that. And how many seats? That's the other thing we need to know. 200 seats in there to apportion. Okay, so this should be pretty easy. So let's do some calculating again. So that means that well, what does that mean for our standard divisor? We'll have standard divisor being the number of people which correspond to a single seat. And our standard divisor, if you remember, we calculated that by taking the total population divided by the number of seats. So this will just be 200,000 divided by 200 seats, and we'll just get a standard divisor of 1,000. That's a nice one to work with. Because now, if we want to calculate our standard quotas, it's going to be very helpful to have a nice and even standard divisor. So let's do that next. Standard quota. Okay, and remember that the standard quota Q sub I is the population of a state divided by the standard divisor. So here, if we do 9,400 divided by 1,000, well, we'll just move the decimal point over 3 places. So 9,000 divided by 1,000 is 9,400 divided by 1,000 is just 9.4. Again, we can just move this over 3 places. We'll get 90.3. Move this over 3 places, and we'll get 100.3. And they should all add up to exactly 1/1000th of 200,000. So 200 seats. Well, perfect. That's exactly what we wanted. We want 200 seats, 200,000 people. Okay. So this is good. And now, how many should we apportion them? Let's find their lower quotas. Those are going to be 9, 90, and 100, respectively. Those add up to what? 199. 199. And so finally, if we want to calculate how many seats each state should receive, using the Hamilton method. So Hamilton apportionment. Each state is going to we have one surplus seat, and the highest fractional part was Bama with 0.4, and all the others had 0.3. Okay. So Bama gets an extra representative, and none of the others do. So 10, 90, 100, and that adds up to 200, and we're good. Okay, so Hamilton's method has not failed us yet. But now I'm going to pose a question. What if the country wanted to have 201 seats in their house? Sorry, I'm blowing on a bug here. In their House of Reps. Well, it is going to kind of throw a wrench into everything, but we could recalculate it all. So why don't we go ahead and do that? I will copy this table over here. And we'll just change some of the numbers. Copy. So let's make a similar looking table here. Paste. And let's simply change up some of the things. So now we want, well, let's erase all of these things. The only things that haven't changed are the populations, right? Our country still has the same population. But now we want the standard quotas to add up to 201. because that's how many seats we have. Okay, so our new standard divisor is going to be the population over the number of seats. It's going to be 200,000 divided by 201. And what are we going to get? This is approximately 995.02. Okay. Now, again, if we remember, if our standard quotas are each state's population divided by the standard divisor, I'll just, well, given that I've got a calculator and you're sitting here watching videos, I'll just tell you what we get when we divide 9,400 by the standard divisor. We get approximately 9.45. And likewise, when we divide the population of Tecos by 995, we will get 90.75. Finally, we divide the population of Illinois by the standard divisor of 995, and we get 100.8. And you can check my math. These things do add up. We're good to 201. Now, lower quotas. Let's round them all down, right? So 9.45 gets rounded down to 9. 90.75 gets rounded down to 90. 100.8 gets rounded down to 100. And when we add all these up, well, we're back at 199. So this time, we have 2 surplus seats, right? So this time, surplus seats. So who are we going to give them away to? Let's see who has the highest fractional parts. Now the highest fractional parts are Tecos with 0.75 and Illinois with 0.8. Bama now has the smallest fractional part. So what does that mean? It means that Bama doesn't get one of the surplus ones. Tecos does. They go up to 91. Illinois goes up to 101. And finally, this does add up to 201, just like it should. Well, you might be wondering, so what? And the so what, well, the so what is exactly here. Look at this. So when there were only 200 seats in the House, Alabama got 10 of them. But once we added a seat, Alabama now only has 9 seats. Now that's strange. If you have more seats in your House of Representatives, as a state, you shouldn't expect your quota, your apportionment to go down. You should expect your representation as a state to go up, if anything, if you add seats. And this is exactly what happened to Alabama. The population of Alabama grew in 1950. This was 1850 to 1911. In 1911, the population of Alabama had grown, and so Alabama was supposed to get an extra seat, but indeed they did not. Yes. Sorry, I'll go back to that when we get to the section 4.6, which is on paradoxes in apportionment. But this is a problem. This is an immediate problem that we only get 9 when there are 201 seats, but 10 when there are only 200 seats. Okay. So this doesn't seem right. When we added a seat to the House, Bama was given fewer seats. So the reason for that is that this method is just a bit deceitful. It seems like it's perfectly fair, but the method actually relies entirely on the residues, on the fractional parts. But the fractional parts aren't the most important. What's actually quite important is what those residues represent as a percentage of the state's population. So a state with a high residue but a low population, a high fractional part but a low population, that fractional part actually makes up a larger proportion of that state's population. So the flaw here is that the method is that Hamilton method relies entirely on the remainders or residues, not what they represent as a percentage of the state's population. In doing so, this method favors states with larger populations. This method is biased against states with smaller populations. And an apportionment method, a good apportionment method, apportionment should be population neutral, as we say. Okay. So that sums up Hamilton's method, what it is, how to use it, and one of the first paradoxes that we've seen in terms of apportionment. And this was a big one when the United States realized this paradox. So, I'll see you next Tuesday. Email me with any questions or post on the discussion board, and I will, yes, I'll hear from you soon.